in the forces chapter of Year 12 Mechanics, you run into questions that look like this, and I've literally never met anyone who likes this question or finds it easy, including myself. I hated these questions when I was younger, and I still don't really understand them properly now, but I found or I was told about a really nice little trick that allows you to do these questions in a much nicer way, at least for me. And so, firstly, though, this is the other example that the textbook gives in this chapter. It only gives two examples, this one and this one. And I've basically, likewise, never met anyone who doesn't just quite like these questions, where you're on a horizontal plane, you've got two particles attached to each other with a string or something, you've got one particle mass 5 and 3, driving force of 40, resistances of 10 and 6, and you've got some tensions in this string, obviously, going inwards like this, that are equal and balanced. And yeah, this is just all very nice, isn't it? You just consider the entire system and do F equals ma. So 40 minus 10 minus 6 is the force, equals the total mass, which is 5 plus 3, times the acceleration. The forces could also include t's, but I just put plus t minus t and they cancel. Of course, you could just work this out, you get a as this. And then that acceleration is equal amongst both of the particles. They're always accelerating at 3 in this scenario here. So what we can do is we can now just focus in on one part of the picture and do F equals ma here. So t minus 6 is the force, equals 3 times a, just because the mass now is just this 3. And you get the t is 15. And again, I've basically always had a good time teaching this, and I think it's really nice, and most people will just pick it up pretty easily. So you just consider the whole system, then you consider part of it. This, on the other hand, I've always hated, and I don't really get it properly, and no one that I teach gets it, probably because I don't really get it. But someone really great pointed out to me that you can just do this completely differently if you want to, and this is now how I'm going to officially teach this from now. You can just ignore this picture, right? So what you're supposed to say is that there's a tension coming up on this rope here that's pulling the thing up. You've got some masses of 0.4 g and 0.6 g going down, because of course you never work on working grams, you want to work in kilograms. What you could do is you could just entirely redraw this picture to look like this. Right, this is a completely equivalent problem. You've got the pan, which you imagine as the leading particle, with mass 0, because it's a light pan, pulling the thing forward with force t. And it's pulling the particle B directly, which then in turn is pulling the particle A. And these tensions in these imaginary strings that I've just drawn in are these questions here. The force exerted on B by A are these tensions. And that's why the book says, oh, you should actually consider the force exerted on A by B. But of course, because we can see that much more clearly why those are the same thing now, because it's just T1 and T1, like they're the same. We know these tensions must be the same, and different to these tensions is this different string. And now we can just do the problem like it's this. We can just pretend it's this. We can do F equals ma on the entire system. This minus this equals the total mass, which are these two, times a, which they've actually already given us in the question, so we're doing this backwards, but that's okay. You can solve that for t, so you get t as that. Then to work out the force exerted on B by A, that's just equivalent to asking what the tension is between B and A in this string here. So we can just focus in on this furthest side bit of the picture here, do T2 minus 0.4 g equals m, which is 0.4 times A, which we still know is 0.5. You work out that tension, that's this answer this bit. And then of course force exerted on B by the scale pan, that's T1. Right, so that we can just work out T1, we can focus on this bit of the picture maybe. Big T is this, minus T1 equals, now this is interesting, the pan has no mass, so it's just equal to 0 times A. And so this means just T1 is equal to that same thing. And we have the entire thing done. I think that's just much nicer than doing it the way that it's intended, because, you know, who amongst us really has any idea what this is actually talking about? But we all love this, so let's just do this instead. And yeah, great.